Before we look at a simple example system and the corresponding root locus, we're going to review a little bit of math and sort of set ourselves up to understand everything that's going on. So the first thing we want to talk about is complex numbers. And so the reason we want to talk about complex numbers is, of course, this S that we have in all of our systems is actually a complex number. So it has a real part sigma and an imaginary part j omega. So remember that our complex numbers can be represented in a couple different ways. So we can represent it as shown here, which would be in rectangular form. But we could also represent this in polar form. So we could represent it with a magnitude, so let's call that m, and some angle, theta. So we could have polar form. And so let's sketch out sort of the relationship between these two on our complex plane. So if we have our imaginary axis j omega and we have our real axis sigma, and so let's say we're at some point that is sigma j omega, so of course we're here, so that would be, again, we've gone over sigma on our real axis, we've gone up j omega on our imaginary axis, and that gets us to our point of interest. So what we're saying is we can also represent this in polar, where our magnitude is the distance to the point from the origin, so this would be our magnitude m, and then our angle is the angle up from this real axis theta. And so of course we can relate the two. So our magnitude m is going to be equal to the square root of sigma squared plus our omega squared, and our theta is going to be the inverse tangent of omega over sigma. And so just as a quick note, you want to be careful when you're using this second equation here for our theta, because sometimes your calculator, depending on which calculator you're using, won't be able to tell if a negative sign is associated with a number in the top or in the bottom. So basically it might mix up. If you have a negative number in the top, instead of putting that negative number there, it might put it here. And you might be asking yourself, well, why is that a problem? And basically it's the difference of going here and down versus going, let's see, here and up. And so, of course, we can see there that those are two different angles, and so we can adjust that by doing plus or minus 180 degrees. Okay, so the next thing we want to talk about is sort of just a general representation of a zero, and so we're not going to use it too much in this unit, but we're going to come back to it in the next unit when we're using our root locus for design. So let's say in general we have this s plus a, which is a complex number. So s plus a is a complex number, and so we can actually represent this graphically with a vector. So a complex number that can be represented by a vector, and the vector is going to be drawn from the 0 to the point where we're evaluating. So from 0 of our function to some point s. And so I know that's kind of vague, but let's consider a specific example then. So let's consider some point s plus 7. I'm going to come down here to this next page. So let's say we have some function s plus 7. And let's say we're evaluating at a specific point at point s equals 5 plus j2. And so of course we could plug in 5 plus j2 for s and evaluate that way, but as I mentioned, when we come to this sort of idea of root locus and using it to design, we're going to want to consider this graphically to sort of help us wrap our heads around what's going on. So to plot this, our s plus 7 means we're going to have a 0 over here at negative 7. And again, that's just the value of s that we would plug in to make it 0. And our point that we're trying to evaluate at is at 5 plus j2, so we go over 5 up j2, and we're going to be at this point over here. And so what we're saying is that this complex number, s plus a, can be represented by a vector that's drawn from the 0 to the point where we're evaluating. So something that looks like this. And so of course this is going to have some magnitude m and some angle theta. And so in this case, we would calculate our magnitude m. That would be the square root of 12 squared plus 2 squared. So the 5 plus 7 gives us 12. Let me clean that up a bit. So the 5 plus 7 gives us the 12. And then, of course, the 2 is the change in height. And so we get that that's about 12.166. And then our theta we get is the inverse tangent of 2 over 12. And that gives us about 9.462 degrees. And again, we'll come back to why that is sort of relevant and useful in a later unit. So that's if we have just one function. So what if we have a function with multiple poles and zeros? So let's say, how do we handle multiple poles and zeros? And so, and or zeros. So I mean, technically we could have just poles and no zeros. And so what we want to do is let's go back to sort of our general equation for an arbitrary function. Of course, ultimately we're going to say this is a transfer function, but for now let's just say it's some function f. And so we can represent that as some gain factor in the numerator times our zeros. So we have s plus z1 times s plus z2 times however many zeros we have. So where z1, z2, and so forth are the zero values. So that's the values of s that make our function equal to 0. And in the denominator, we have s plus p1 times s plus p2, so on and so forth. And again, our p1, p2 are going to be poles of the function. And so that is, if we plug in s at a value of p1, p2, or any other pole, our function is going to equal infinity. So what we can do is we can rewrite this a little bit, and we can change this to have each zero or each function in terms of a magnitude and angle, similar to what we did up here. So we can say we still have this gain factor out front, but now instead of a 0, 1, let's say we have magnitude associated with 0, 1, angle of theta 0, 1, and we're multiplying that by our 0, 2, so we have magnitude of 0 for 2, angle with theta z2, and we have that same thing for however many zeros we have. Similar thing in the denominator, we're going to have magnitude for pole 1, angle theta p1, and magnitude of p2, angle with theta p2, so on and so forth for however many poles we have. Okay, and so again, all I've done is sort of switch to this polar representation form as opposed to our standard zero and pole representation. So now we can use sort of the basic definition of our complex numbers, which I've not gone over here, but you should have seen somewhere else. So ultimately we know a complex number is basically an e to the j something, so it's an exponential term. So because of that exponential property, we can rewrite our f of s in this form. So we can say our f of s is going to be some general gain k out front, and then we're going to be multiplying that, and we want to have sort of one polar number in the numerator, and so it turns out that we just multiply these magnitudes. So we have mz1 times mz2, so we have the product of all of our magnitudes. And for our phase angles, again, keep in mind these are exponential, so it's e to the something. So we're multiplying the magnitudes, and then the argument, which is our angle, is going to be added in this case. So we have theta z1 plus theta z2 plus so on and so forth. And same sort of approach when we're dealing with our poles in the denominator. We're going to have the product of the magnitudes, so mp1 times mp2, and that's going to be angled with the sum of the angles. So theta p1 plus theta p2, so on and so forth. Okay? And now we can simplify this one step further by saying our f of s is equal to this general gain k. And now if we want to simplify this to one single polar number, all we have to do for the magnitudes out front, we're just going to take that quotient. So we're going to have our mz1 times mz2 divided by our mp1, mp2, and then all of that is going to be angled with, and we're going to take this angle in the numerator and we're going to subtract the angle in the denominator. And again, all of this comes from the properties of our exponential function. So we have then our theta z1 plus theta z2 so on and so forth, minus the sum of our pole angles. So P1 plus P2, so on and so forth. And then let's close all of our brackets there. And so if anybody has any questions about some of the stuff I'm glossing over with our complex numbers, feel free to let me know. Ultimately, we're not going to have to worry about this too much. But again, if you have questions, definitely let me know. The book does describe this a little bit differently. So if you look at equations 8.4 to 8.6 in the textbook, they're basically saying what I'm saying here. Personally, of course, I think what I'm showing you is a little more clear, but if you want to see a different representation of that, you can look at these equations in the textbook. If you want to get some practice using these equations or seeing these relationships, you can look at example 8.1, which is on page 309 of the 8th edition textbook.